So, hi everyone, welcome to today's session. Hope you can all hear me clearly. Today we are going to complete the deep learning intro and then you can go ahead and practice more using the Keras library. So there are a few datasets I've shared with you, and those datasets are some of the inputs that we will use here. But before that, let us understand how we create our deep learning models. So from our last class session, we had this. So this is the first step in creating deep learning models. So we first start by importing from TensorFlow, import Keras. Then from TensorFlow.keras import layers. So this allows you to create your TensorFlow layers. So this is the input units, the input layer, and the output layers. And here we mentioned that, for example, if we want a planning model with a single layer, so this is what we do. So we define our model and we say, let our model be equal to layers.sequential. You open brackets, open square brackets, then define your layer. So we will have layers.dense. We specify our units to be equal to 1. So when we specify our units to be equal to 1, this means that this is our output layer. And then the input shape defines the number of features that we have in this data set. Okay. So this is a single deep learning model. So with a single layer. But if we want to include more layers, this is what we do. So we type in layers.dense, then we define our units here being equal to 3, then the input shape, which defines the number of features we have. Then we have our hidden layers, and then we have our output layer. So the next thing we are going to see next is, apart from adding the input layer, the hidden layers, and the output layer, so what are some of the additional things we can add into these layers? So let's go back to our presentation and I'll come here. So deep neural networks. So let me present and then we can proceed. So this is how our layer looks like. So neural networks typically organize their neurons into layers. When we collect together linear units having a common set of input, we get a dense layer. So these are those hidden layers, so which we call also the dense layers. You can think of each layer in a neural network as performing some kind of relatively simple transformation. Through a deep stack of layers, a neural network can transform its input in more and more complex ways. In a well-trained neural network, each layer is a transformation, getting us a little bit closer to a solution. So each and every layer that we have here, or each and every neuron that we have in here, gets us closer to predicting this value, for example, for y0 or y1. So some of the things that we can add to our hidden layers are the activation functions. And how do the activation functions help us? So they make sure that what we are trying to predict is not the same thing that we usually get, but it ensures that what we are trying to predict is actually closer to the actual value. So it turns out, however, that two dense layers with nothing in between are no better than a single dense layer by itself. So if we go back to this code, so this single layer or this model up here is the same as what we have here. So the output that you are going to get up here is the same output that you are going to get down here. And what's the reason as to why this is so? It's because we are going to be getting the same output because we've excluded the activation function. And what is an activation function? An activation function is simply some function we apply to each of the layer's output. So the most common is the rectifier function. So the rectifier function is usually called the ReLU function. And what does it do? So it maximizes the value to either be a 0 or the lowest positive x value. So the rectifier function has a graph that's a line with the negative part rectified to 0. So you can see here, any value that is on the negative side is rectified to 0. And any value that is on the positive side is taken as it is, okay? So when we watch the rectifier, when we attach the rectifier to a linear unit, we get a rectified linear unit or ReLU. So this is the activation function that we usually use. So applying a ReLU activation function to a linear unit means the output becomes max 0. So if your prediction is negative, then you place a 0 there. But if it's not negative, you take your weight, multiply it by x, then you add the bias term. So this is how it looks like. So fitting an nonlinear relationship data. So for example, here in your data, so if you were to fit this data that is over here, if you were to fit a linear regression model, so we will get a straight line that passes through this scatter plot. But if we add an activation function, you can see we get a U-shaped line, so which tries to predict negative values and also predict positive values, giving us this U-shape. That clearly explains the relationship that we have between x and y and giving us almost accurate values here. So how do we add the activation functions to our data? Okay, so what we do is here in our code, what we usually do is we say, after defining the units, we type in activation and we specify the activation function we are going to use. So for example, here we can use the ReLU function. Another thing you need to note is, so I can delete this because you know what the units being equal to 1 mean. So there should be no activation function for this layer. And this is only applicable in regression tasks. So for classification tasks, we should add an activation function here. But for all the other layers, we can add an activation function. And this is how we do it. So this is the recommended method, but there is a second method. So this is our first method. So remember, we are only discussing this model part, and we are discussing how the model part is defined and some of the things that make up this model. So first of all, we've looked at the layers part and what these layers represent. So if we check, maybe there is this diagram. So we have the input layers defined by the input shape. We have the hidden layers defined by this part here. So you can add multiple hidden layers. And then we have the activation function. So these L-shaped lines that are inverted being our activation functions here. So for example, ReLU. And maybe this plus sign here being our output layer, which is this part that we have here. So it's that simple. So we add an activation function, and an activation function ensures that we cover all the trends that are there in the data. So for example, if we have negative values in the data, it ensures that we don't get a straight line, but we get curves that can be able to, that we can use to make predictions. So that's how we add the activation functions. And then another thing we have is the stochastic gradient descent. So what do we mean by that? So in the first lesson, we learned how to build fully connected networks out of stack of dense layers. When first created, all of the network's weight are set randomly. So actually I can show you how that works. So we will go back to this notebook that we have here. I'm going to click on connect, and then I'm going to upload the data that I shared with you on WhatsApp. Okay, just a minute. Let me upload that data and then we can proceed. So the data is ready. If I run this, then if we go to this part here where we have this simple model. So this is a simple model where we have a single layer. So what you will notice is if we plot the weights for this single layer, is you will notice that the weights keep on changing. Okay, so if I run this now, okay, so let's import Keras first. Let's run that. Then I'll go down to this part where we plot our model. So if we run this, you can see this is the first line that we get. And if we run this cell again, the line will change. So you can see it has changed. So it means that these weights are being generated at random. And since we are generating these weights at random, it means that our predictions will also be random, because we know that our prediction is W multiplied by X plus P. So if W is random all the time, it means that the kind of predictions that we will be getting each and every time we run our code will be different predictions or different outputs. So what we need to do is we need to fix that and ensure that the predictions that we are making, so here for this part, y is equals to model.predict, we need to ensure that the values are same all the time. So this is the code that we are using here. So we define our model, then we create our sample X dataset, and our sample X dataset has values ranging from -1 to 1, and we have 100 values in there. Okay, and then what we do is we create our Y, and our Y is equal to model.predict, then we predict on X, and this is the model that we created. So this model that we created over here has not been fitted to any dataset yet, but you can see that the weights are always random. So how do we fix this? So we fix this using the stochastic gradient descent. So as with all machine learning tasks, we begin with a set of training data. Each example in the training data consists of some features together with an expected target. So training the network means adjusting its weights in such a way that it can transform the features into the target. Okay, so for example, if we have the 80 serials dataset, for instance, we want a network that we can take each serial sugar, for example, fibers and protein content, and produce a prediction for that serial calories. So this was the first example we had in class where we did these calculations manually and we never knew how we define these weight terms. But now here we are discussing how we get that W. Okay. So if you can successfully train a network to do that, its weights must represent in some way the relationship between those features and that target as expressed in the training data. And these Ws or these weights should not be random. So in addition to the training data, we need two more things. So for us to ensure that we get correct results, we need to add two more things. And that's a loss function. And a loss function is something like an accuracy check. So we check like how accurate is our model, and an optimizer. So an optimizer is used to adjust those weights based on the accuracy you get. And we'll get to see how we add those to our model. So we have the loss function. So we've seen how we design the architecture of our neural network. So this is how we define the architecture of our neural network. So this we say our model should be equals to that. We add our layers, specify the units, include the activation function and the input shape. So this is the first layer, then the dense layers, and then the output layer. So you already know how you do that. So what we need to add now is the loss function. So we haven't seen how to tell a network what problem to solve. So we've defined a model, but does the model know what kind of problem it's solving? So is it regression? Is it classification? So that's the job of the loss function. So the loss function measures the disparity between the target values and the values the model predicts. So different problems call for different loss functions. So for example, if we are dealing with a regression task, we can use the MAE. And if we are dealing with a classification task, we can use the accuracy score. So this is how the MAE works. So you can go through that later on. And next we are going to look at the optimizer. So we've described the problem we want the networks to solve. So using the loss function. So once you've known the problem you are solving, so for example, if it's classification or regression, you need to add an optimizer that will be used by the model to adjust the W values, and those are the weights. So we've described the problem we want the network to solve, but now we need to say how to solve it. So this is the job of the optimizer. The optimizer is an algorithm that adjusts the weights to minimize the loss. So virtually all of the optimization algorithms used in deep learning belong to a family called stochastic gradient descent. So they are iterative algorithms that train a network in steps. So one step of training goes like this. So sample some training data and run it through the network to make predictions. Then measure the loss between the predictions and the true values. And then finally adjust the weights in a direction that makes the loss smaller. And then you rerun the model till you get an even lower loss. So this is how it works. So for example, this is our fitted line. So if we start here at the training loss, you can see that each and every time this model runs, it gets to adjust its weights. So you can see these two lines. So we have the brown and the green line, whereby the values for W and B keep on changing for each fit that we make. And then you can see here, the training loss keeps on reducing with each and every fit that we make. And then the line of best fit keeps on changing until we have something that looks more better. Okay. And that's it. So another thing we can add to our model is the learning rate and the batch size. And let's see how we do that. So I'll go back to this notebook that I've shared with you. And here you can see we have sample model that has been we have a sample model that has been instantiated. So if we scroll down after you've added your activation function, what you usually do next is you add your optimizer and your loss. So I'll copy this and I'll paste it here on the other side. So this is how you do it. So once you've instantiated your model, so maybe I'll say this is our model. What we do is we type in model.compile and then we add our optimizer. So for example, we have the Adam optimizer. So we can Google other optimizers that are there. So we can check deep learning optimizers. And you can get a list of deep learning optimizers that we have. But I guess I've included some here in the presentation. Okay. Then another thing we add is the loss function. So since, for example, if we are dealing with regression, we can use the MAA as our loss function. So this is basically how we add our optimizer and the loss function. So after adding the optimizer and the loss function, we now know that we are dealing with a regression task, and this is how we will adjust the weights in order for us to achieve the goal that we want to achieve, and that is maybe predict prices of a house, for example, using a deep learning model. So what we usually do next is we usually add the learning rate and the batch size. So here you can see, like for example, we say you notice that the line only makes a small shift in the direction of each batch instead of moving all the way. The size of these shifts is determined by the learning rate. Smaller learning rate means the network needs to see more mini batches before its weight converge to their best values. So learning rate is just like the amount of data this model is going to see each and every time it runs. So you can see, for example, here, when the model is running, you can see we have this curve moving in a way that I can say it's looking at some sample data. So for example, 20 sample inputs and then adjusting, looking at another 20 sample inputs and then adjusting. So those are the batches. Then the learning rate and the size of the mini batches are the two parameters that have the largest effect on how the stochastic gradient descent training proceeds. So their interaction is often subtle and their right choice for these parameters isn't always obvious. So there is a way in which you don't have to select the learning rate yourself and the batch size. So what you can usually do is, if we go back here, is we can copy this but for history. So after compiling the model, after adding the optimizer and the loss function, what we usually do next is we create a variable called history, and history will contain all the details that are there in our model. So here we add the batch size. So the batch size is the number of data points we will include in each training, and the epochs are the training steps that we will have. So how many trainings we will have? So for example, 200 epochs means that we are going to have 200 different fits until we've trained all these batches. Okay, so that's what we mean. And then after defining this, we need to make sure that, so for example, if we go back to our presentation, we need to make sure that our model doesn't do all these fits to the end, because if it does all those fits to the end, it means that this training loss will always be reducing. And if it's always reducing, there are chances that we are overfitting. And what is overfitting? So overfitting means that our model is learning from noise and it's not learning from signals. So we have two things that we need to check when training our model. So I'll explain that using this curve here. So I don't know if I can draw here, but I'll try. So for example, here we have these, just a minute. So I'll say we have this line here. So anything that is on the left hand side is noise. So this should be my right hand side. So anything that is on my right hand side is noise, and anything that is on my left hand side is signal. So it means that if we are fitting a model and this is our training data, it means that the loss will always reduce because your model is learning from both signal and noise. And that's the case over here, because you can see the loss is always reducing and not rising. But if we maybe include a test set, you can see that the loss will always reduce in cases where the model is learning only from signal. And signal, these are the parts of the data that clearly represent the trend that you have in your data. And then noise, these are those things that make no sense but can reduce your training loss. So if your model has fully learned from all the signals, then the loss will reduce. And if the validation loss starts to rise, then it means that your model is learning from noise. And this is basically what we have. So like a diagram representing underfitting and overfitting. So this is how overfitting looks like. So we have the fitted curve, which tries to be perfect, but that should not be the case. And for underfitting, we have this line that doesn't cover all parts of your data. So what you can do to avoid overfitting and underfitting is you can make your model wider or you can make your model deeper. So I'll let you go through this. And another thing you can do is you can do the early stopping. So I'll show you how we add the early stopping for model fitting. So since I've shown you how you instantiate your model, how you compile your model, and how you fit your model, the next thing I'll show you is how you add the early stopping, because that's the next most important thing. So to add the early stopping is, if we go back to this code that I shared with you, if I scroll down here, so just a minute, there should be a variable called early stopping. So this is where we define early stopping. So I'm going to explain each and everything that we have here. Yeah, so we have to import early stopping again as from TensorFlow. So from TensorFlow.keras import callbacks, then we are going to define our early stopping. So early stopping should be equal to callbacks.early stopping. Then we have the minimum delta. So the minimum delta is the minimum loss amount or the minimum loss change that we should have before saying the model is learning from noise, or before us saying that this validation curve has started to shift its direction. Okay. And then we have the patience. So how many epochs to wait before stopping? So here you can see, for example, we defined 200 epochs. So how many of these 200 feeds should we wait before checking this loss value? Then restore best weight means if we are fitting this model. So for example, if the 20 fits end here at this part, should we pick this last score that was lower, or should we pick this next score that was higher? So if it's true, then we pick the last score that was lower. And that's basically how we do it. So after creating our early stopping variable, what we do next is we feed our model again. So we say let our history be equal to x comma y. Then we create the validation data. So you have to, so maybe I'll use the x train and y train, and then you have to include your validation data. So that's the x test and the y test data. So you already know how you create the x test and the y test data. Then you have to specify your batch size. So we can use 128 that we are using in this class example. And then epochs we can use 200. Then you have to specify the callbacks, which will specify the early stopping, so that we will avoid the overfitting part. So that's it for that part. So the last thing that you need to know on this part, so before we go to the last thing, let's try understand what we've been looking at. So the first thing is model instantiation. So for model instantiation, we create our layers. So we have the input layer, the dense layers, or what we call the hidden layers, and then we have our output layer. Then after that, we specify the kind of task we are doing. So if it's regression, we can maybe add our loss here and say MAE should be our loss function. If it's classification, we can change this from MAE to being accuracy. Then optimizer. So how do we adjust our weights? So we can use the Adam optimizer. So Adam optimizer does a good job in changing the weights to reduce the loss value here. And then what we usually do next is we feed our model. Then we specify our features and our target variable. Then we specify the batch size. So batch size is the amount of data you are going to fit in each and every feed. And then the epochs, here are the number of feeds you are going to have. Then apart from this, we can add early stopping, and early stopping is just for us to avoid overfitting. And that makes us change this part for fitting our model. So the last thing we are going to look at, and it's somehow a data pre-processing part, is this part here, dropout and batch normalization. So when we talk of dropout, we mean that we are going to drop some hidden layers, because if these layers learn from each and every previous neuron that we have, there are some bad behaviors that are going to be maybe copied from the previous neurons. So let's see what we have here. So there is more to the world of deep learning than just dense layers. There are dozens of kinds of layers you might add to a model. Some are like dense layers and define connection between neurons, and others can do pre-processing or transformation. So this kind of layers that we are going to look at are the layers that do reprocessing or transformation. So here we will learn about two kind of special layers, not containing any neurons themselves, but that add some functionality that can sometimes benefit a model in various ways. So the first layer we are going to look at is the dropout layer. So the idea behind dropout is to break down conspiracies. Okay. And what are conspiracies? So these are spurious patterns that a network will often rely on in order to like make predictions. So for example, if your child learns something bad from school and your child goes ahead and meets another kid who is maybe joining the school today. So he's going to like show that kid what he usually does. But for you to avoid that, you need to like separate them, right? And maybe this new kid needs to like learn new behaviors from another kid. So your kid can teach other kids some good behaviors, but when it comes to like field work where he performs badly, you can maybe exclude him there and involve other kids in like training that part of the field. So that's how dropout layers work. So you can see this visualization. So this is a visual representation of how dropout works. So for example, for input x0, we can have its input go to this top hidden layer and the second hidden layer. But for these two other layers, we can exclude them so that those other two can have inputs from x1 and x2. So these three other hidden layers here will have some basic information concerning x0 from only two hidden layers apart instead of getting these input from four, so that any patterns that were there in these two hidden layers will not be there in the other two hidden layers because they've not seen x0, so they don't know what happens in x0. So how do you add the dropout layers? So if we come back to our model here, so this is how we do it. So if we've defined our model, what I'll do here is I'll type in layers dot drop. Then after typing layers dot drop, you define the rate. So it should be dropout. Then rate should be equal to, for example, if it's 50%, you type in 0.5. So that's how you add the dropout layers. And you can only add the dropout layers in cases where you are dealing with hidden layers. So if it's the input layer, you can't add the dropout layer before that. Then another thing we can add is the batch normalization. And batch normalization is just the scaling of your data. So just like standard scaler, because we've not seen the part for scaling data in deep learning, we can use batch normalization to scale our data. So it's the same thing we do when we say we are using standard scaler in a sklearn or min-max scaler. So what we do is we type in after dropout, we type in layers dot batch normalization, and that should normalize your data. Okay, so I'm confirming to see if the code is okay, and I guess everything is now okay. So that brings us to the end of today's session. So it has been long, and I've tried my best to explain each and everything that we have here, both theoretically and practically. So what I'll do is I'll give you guys time to go through this other notebook that I've shared with you, and also go through the presentation again and understand how deep learning works. So I've shared the data set with you. So what you need to do is just go ahead and upload it here, and then rerun all these cells, reading the comments that I've added here. So you can try and understand what I've explained in this short notebook here. So these are the most important things that you need to know. So the rest of the things that we have here, so for example, this part that we have here, we've already covered that in class, like splitting the data into training and test set. We've already covered that in class. Yeah, so that's it for today. I guess I'll see you again on, let's meet again on Wednesday so that we can fully finalize this. So maybe do a quick Q&A and then head over to the model deployment part. Yeah, so that's it from my side, not unless you have questions.